Okay, we start our first video in all of the equations with the equations of chemistry. And we start with moles and molar mass. And what does it have to do with this rather sweltly looking guy here? So here are the equations that we are going to be using. The NCEA in New Zealand, the equation n equals little c times little v. In the International Baccalaureate, it suddenly becomes n equals big C, big V. It's the same C. And in the Australian exams, it's rewritten in this form here. If you have a look at it, this equation here is the same as this equation here. They're both equivalent. The n is the subject and C is the subject here. The other equation is little n equals big M, little m over big M. It's the same here for the International Baccalaureate, but something kind of curious happens here. In the Australian exams, n equals little m over mm, and mm means molar mass. Okay, so the first question we need to ask is, what is a mole? And what does it have to do with this guy here? This rather sweltly looking guy, Avogadro. And by the way, his name is Avogadro. My computer spell check keeps trying to tell me that his name is spelt Amadeo Avocado. It's not. So what is a mole? Well, when you think of a mole, you might think of this thing, or maybe even this thing. Well, that'll be true, but the mole that we're talking about is related to Amadeo Avogadro in this way. And I think around about 1801, I think it was. I'm sure someone, if that when they find out, will correct me if I'm right. 1801 or 1802. He came up with a hypothesis, which has since been turned into a law or a rule, really, because it's not hard and fast. Is that in the same conditions, that is temperature and pressure, the same number of atoms and molecules occupy the same volume. And this came to be called Avogadro's law. It's really a rule because it kind of breaks down, but we'll presume that it's correct. And this left us with a bit of a problem. Atoms are really, 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 really tiny. So it makes absolutely no sense whatsoever to sort of talk about one atom and another atom. So after a long, long time, and it wasn't until 2019 that Avogadro's number was actually settled upon, we decided that 1 mole is equal to the number of carbon 12 atoms in 12 grams of carbon 12, roughly. It wasn't quite measured like that. It was measured actually using silicon, but this is the basic theory. So why is that important? Well, we can actually measure that. And what's more, carbon 12 is very stable. It's abundant. There's lots of it. It's pretty easy to isolate. That is, to make a pure amount of that substance. And it's really cheap. So that's why we decided really on carbon 12. We did use oxygen, we used hydrogen, and we played around with different scales for a long time. And Avogadro himself never knew what the number was, but we named it after him. Science likes naming things after people. So what is that number? It's a really, really huge number. The number that we're going to use in these videos is the number 6.022 times 10 to the power of 23. It's actually 6.02214 something. And in 2019, it was decided that we're going to say, okay, this is Avogadro's number. There we go. So if we have a sort of magic chemistry box here, and we had exactly 12 grams of carbon 12 in there. So carbon 12 is in there, exactly 12 grams, nothing else, nothing more. There would be 6.022 times 10 to the power of 23. Now that is a huge, huge, huge number. But atoms are really, really, really tiny. So that's why we had to choose such a huge number. And it's accepted now as part of the System International, the metric system, that is our measure of a mole. Okay, so why would we want to choose a number and not a mass of something? It's because all reactions at the end of the day are reactions, at least according to kinetic theory, which is being accepted since this theory was put forward, that reactions happen between individual atoms, either bond or break apart. So imagine that we had one atom of element A, and we had one atom of element B, and we added them together and we made the element AB. It would be just two atoms coming together to forming a new molecule. So there is one atom of A, one atom of B, one molecule of AB. Obviously, each of those atoms is way too small to measure. We can't even see them. They're just so tiny. So we choose a mole of that. So in our magic box here, say we had, let's remove the carbon 12, say we had 6.022 times 10 to the 23 numbers of A, and also in that box we put in 6.022 times 10 to the power of 23B, and we waved our magic wand, and every single one of the A's bonded with every single one of the B's, just A to B. There's no monkey business going on. There's no AAB or ABB or anything like that, and there's no spare ABs left over. We would have 6.022 times 10 to the 23 molecules of this AB stuff. And here we have balanced a chemical reaction. So the coefficients here at the front, you can take it as being a proportion of each other, but the proportion of moles. So if we had 23 moles of A and we had 23 moles of B, a perfectly 100% yield reaction of those two would be 23 moles of the molecule AB. If all of the A's and all of the B's all matched up together in this exact proportion. Fantastic. So 6.022 times 10 to the power of 23 of any of individual atoms or molecules or ions or isotopes are a mole of that subject. So this is really, really important. Most of the time when you come to do stoichiometry, which is the mathematics of reactions, you're going to be working mole to mole, and it's always a good idea if they give you something, a mass of something, to convert that into moles, because it's only moles that matter. Okay, let's say, for example, that we had 1 mole of gold, and I know that atoms don't actually look like that, but we'll pretend that they do. We have a gold atom here and a hydrogen atom here. This one atom of hydrogen is almost 200 times smaller than this atom of gold. The masses are pretty incredible. Well, the comparative masses are pretty incredible. So if we had 1 mole of gold, it's going to, if we put it on a pair of scales, and I'm going to pretend that weight is the same thing as mass. I know that it's technically not, but we're going to pretend that it is. This 1 mole of gold is going to have a mass of 196.97 thereabouts grams. This 1 mole, so 6.022 times 10 to the power of 23 of these hydrogen atoms would weigh around about, well, would have the mass of around about 1.008 grams. And we're going to get to the reason why it wouldn't have exactly 1 and this doesn't have exactly 197. So it would make absolutely no sense if we were trying to do these things by mass, as we had 1 gram of gold and we had 1 gram of hydrogen. We're going to run out of the hydrogen way, way, way sooner than we run out of the gold. Actually, no, it's the other way around. We will run out of the gold way, way, way sooner than we would run out of the hydrogen, because 1 gram of this is there are 200 times more hydrogen. So it doesn't make a lot of sense. We have to convert things to moles. Always convert things to moles. If you need to do reactions, it must be in moles. Okay, so let's break down what we are going to be using for our equations this time out. I'm going to be using the NCEA versions purely because the students that I have are doing NCEA, so some of them do International Baccalaureate, but we're going to be using NCEA. Okay, N. So N is just the number of moles of a substance. Okay, so if we have a certain amount of stuff, we're now in effect saying how many molecules or how many atoms of the substance do we have. And this is going to be a member of the real numbers set, which is equal to or greater than 0. So it doesn't have a unit, it's just a number. So you can't have negative moles. I can't imagine how you would have negative moles. Antimatter, I don't even know much about antimatter, so I can't really say whether they measure that in antimoles. Okay. C here, little c, which becomes big C here in International Baccalaureate, is the molar concentration. So this is the amount of moles of a material in 1 liter of a solvent or something that's dissolved into. So just as a side note, 1 liter, LITRE, if you're in the United Kingdom, pretty much everywhere except for the United States, is equal to 1 decimeter cubed. And I know that the International Baccalaureate wants the decimeter expressed in that way. So deci means 1/10, so that would mean 10 centimeters by 10 centimeters by 10 centimeters, which is going to be 1,000 cubic centimeters. Sorry, not one cubic centimeter, 1,000 cubic centimeters, or 1,000 mils. Okay, so 1 liter is equal to 1 decimeter cubed. IB seemed to be quite hung up on that. All right. Volume. Big V is volume. And that's going to be measured in liters. So I guess this one is going to be, concentration is going to be moles per liter. The volume is going to be in liters. So big L. All right. We get then to little m. Little m is the mass. And that's going to be most of the time measured in grams. If you see it in kilograms, usually you're going to need to convert it to grams if you're doing chemistry. It's a bit of a distinction between chemistry and physics. Physics tends to be in kilograms. Chemistry tends to be in grams. And now we get to big M. So big M is the molar mass. And it's the reason why the Australian exams have it capital M, capital M. Molar mass is expressed in grams per mole. So we already did one here with the gold and the hydrogen. If we had 1 mole of gold, it would weigh 196.97 grams. So that is the molar mass of gold. And here 1.08 is the molar mass. Well, it's not quite actually. It's the relative molar mass of hydrogen and gold. So this is expressed in grams per mole. All right. You should be familiar with this. This shouldn't be the first time looking at a periodic table. Most of the time we are going to use this relative atomic mass interchangeably with mole mass. They're not quite the same. The relative atomic mass takes into account that not all elements are in their sort of standard isotope. So hydrogen, which of course has 1 proton, can have 0, 1, 2, I think even 3. They're really, really unstable, but these are different isotopes. So this number that we have here, so neon has an isotope of 20.2. It means that most of the time it has a molar mass of 20, but sometimes there are isotopes where there is an extra neutron in there. So that's why it's not quite exactly 20. And a lot of these are not nice numbers, but there's beryllium, carbon, nitrogen, and oxygen, and helium. To 1 decimal place at least, they do have a relative atomic mass of a whole number. Okay, let's do a few examples, a few questions to get you in the hang of using these equations. Okay, we're asked to calculate the number of moles and 2.5 litres of sodium chloride solution with a concentration of 0.5 moles per litre. So first off, let's look at what we've got. We've got 2.5 litres, so it's already SI units. So capital V is going to be 2.5. We want to calculate N. We don't know what that is. And we're told that the concentration is already in SI unit, 0.5 moles per litre. So C is 0.5 in every 1 litre. That's the worst zero I've ever written. Okay. Fixed. Do we have anything else? No, we don't really care what the mass is. So we're just going to be using this one here, and we're going to be rearranging. Well, we don't even need to rearrange it. It's already in the order that we want. So N is CV, which is going to be 0.5 times 2.5, and it's going to be 1.25 moles. And we're done. Next off, we're asked to weigh out 100 grams of calcium carbonate. How many moles is this? Well, we have a little bit of a problem here. We're going to need to do something first. So we've got 100 grams. So we've got little m, and it's already in our good SI units. How many moles is this? So we are looking for N. So now we need to find the molar mass. The molar mass of CaCO3 is going to be equal to the molar mass of calcium plus the molar mass of carbon plus 3 times the molar mass of oxygen. So we will go to our periodic tables. So calcium is 40.1. Carbon is, of course, 12 by definition, plus 3 times the molar mass of oxygen. Molar mass of oxygen is 16. And then we will grab our calculator and solve it. So 40.1 plus 12 plus 3 times 16 is 100.1. Okay. So the number of moles is the mass, which is 100 divided by 100.1. So it's going to be some number really, really, really close to 1. So 100 divided by 100.1 is 0.999, which we say is 1.0 using our to one decimal place rule. And that's that one done. Next, we're told that a student needs exactly 3 moles of magnesium oxide, MgO, for an experiment. How many grams should they weigh out? Let's look at what we've got and what we're looking for. So we're told that this student has 3 moles, so N equals 3.0. We're looking for grams, so we're looking for the actual mass. So in order to find that, we need to use this equation, but we need to find the molar mass of MgO. So the molar mass of MgO is going to be equal to the molar mass of magnesium plus the molar mass of oxygen. There's 1 atom of each per molecule. So the molar mass of magnesium is 24.3 plus the molar mass of oxygen. We worked it out last time. It's going to be 16. And when we add those together, we don't want to do that. We want to do this. 24.3 plus 16 is 40.3. So there are 40.3 grams per mole of magnesium oxide. Now we can solve for M. So N equals little n over big M. So 3 is going to be equal to the mass, which is unknown, divided by 40.3. And now we want to multiply both sides by 40.3. It's now an algebra problem. So M is going to be equal to 3 times 40.3. And that's going to be, so 3 times 40 is 120. 3 times 0.3 is 0.9. So 120.9 moles. And that's that one done. So now we're told that 0.2 moles of solute are dissolved in 500 milliliters of water. What is the concentration, C, of the solution? So let's look at what we've got. We've got the number of moles, which is 0.2. And we're told that this is dissolved into 500 milliliters of water. But if you remember, milliliters is not the unit we want. The unit we want is liters. So 500 milliliters would be 500 times 1,000th of a liter. So that's going to be, the volume is going to be 0.5 liters. And we're looking for the concentration. Which equation are we going to use? Clearly we're going to use that one. So N is going to be equal to C capital V. So that's going to be 0.2 is going to be equal to concentration times 0.5. So if we divide both sides by 0.5, and now it's no longer a chemistry problem, it's an algebra problem, those are going to cancel. So the concentration is going to be 0.2 over 0.5. So the concentration is going to be 0.4. So 0.4 watt, 0.4 moles per litre. So an unknown metals sample has a mass of 24.3 grams and contains exactly 1 mole. Using the data list above, which is the periodic table, calculate its molar mass and identify the metal. So we're going to presume that this metal is a pure metal and it's not an alloy. So let's go to our periodic table and look for 24.3 grams. And it has to be a metal. And here we have our winner, magnesium. Are there any more? Nope. So that means our winner, chicken dinner is magnesium. So on this one, we want to make a solution. So you weigh 20 grams of sodium hydroxide, NaOH pellets. You dissolve them in enough water to make 2 liters of volume. What is the final molarity C? Molarity is another word for molar concentration. So you weigh 20 grams. So our little m is 20. And you dissolve them into 2 liters. So V is going to be 2.0. Okay, what are we actually looking for? We're looking for C. C is what we don't know. We need to find the number of moles. So N is unknown, but C is what we're actually looking for. So we're going to need to use this one first and then use this one second. So the mass, this should actually be a little m. It doesn't look like a little m, but it's a little m, and we need to find big M. We need to find the big M of NaOH, and that's going to be the molar mass of sodium plus the molar mass of oxygen plus the molar mass of hydrogen. So the molar mass of sodium, if we grab our periodic table, is 23, plus the molar mass of oxygen is 16, plus the molar mass of hydrogen is 1. Should be a bracket there, plus 1. So what's it going to be? 17 plus 23 is going to be 40. So this is going to be 40 grams per mole. Now that we've got that, now we can use this equation here to work out how many moles of the substance that we have. So if N equals little m over big M, that's going to be equal to 20 grams over 40 grams per mole, and that's going to be equal to 0.5. So N equals 0.5. Now we can use this one here to work out C. So N equals CV. We know that N equals C times V, and we know that N is 0.5, so 0.5 is going to be equal to the concentration times this volume, which is 2.0. So C is going to be equal to 0.5 divided by 2, which is going to be equal to 0.25 moles per litre. Next, we're told that we have 500 millilitres, so we're going to need to change that straight away. That's going to be 0.5 litres, 0.5 litres of copper sulfate with a concentration of 1.0 moles per litre. So that's our C. If you evaporate all the water, what is the M mass of the solid copper sulfate that will remain? Okay, so first off, we need to work out how many moles of this copper sulfate we have. So the number of moles of this copper sulfate is going to be equal to the concentration of this, which is 1.0 times the volume, and the volume is 0.5 litres. So the concentration is times 0.5, which is 0.5. So C equals 0.5. Okay. Sorry, the N is 0.5. So then we can come along to this one here and work out the mass. So in order to work out the mass, though, we're going to need to work out the molar mass of that. So the molar mass of copper sulfate is the molar mass of copper plus the molar mass of sulfur plus 4 times the molar mass of oxygen. So the molar mass of copper is, where is our copper? Where's our copper gone? 63.6 plus the molar mass of sulfur, which is 32.1, plus 4 times 16. We've used the molar mass of oxygen a lot. Let's work that out. Okay, so 63.6 plus 32.1 plus 4 times 16. Let's move this so you can see it. And that's going to be 159.7 grams per mole. And now we're going to use this one here to find what the little m is. So if n equals little m over big M, then 0.5 is going to be equal to little m divided by 159.7 grams. So the mass of this is going to be equal to 0.5 times 159.7 times 0.5 is 79.85 grams. And it's our final answer. So we wander into the lab and we want to do a reaction. The reaction requires 0.5 moles of hydrochloric acid. We pick up a bottle on the shelf, a 1 litre bottle, and it is labelled 2.0 M. What volume of this acid should you measure out? So there is a trap here. If you look at it as 2.0 M, it doesn't mean 2.0 moles. It means that the concentration is 2 moles per litre. So the concentration is 2.0 moles per litre. So we require N to equal 0.5 moles, and we want to know the volume of that. We don't really care what the molarity is. We only really care about how many volumes of it we need. So, which one are we going to use? We're obviously going to use this one. Okay, so 0.5 is what we're looking for, and we know the concentration is 2.0 times the volume that's required. So we're going to divide both sides by 2.0. Sorry, 2.0, not 0.2. So the volume is going to be 0.5 divided by 2, which is going to be 1/4, 0.25 liters of the substance, of the hydrochloric acid diluted. So, which contains more individual particles, moles, 10 grams of water, or 10 grams of ammonia, NH3? How are you going to work that out? Well, we're going to use this formula here, and we want to work out N for each. So we need to work out the molarity of both the molar mass of both of them, and then find the N for each one. The actual mass, the gravitational mass, is the same. It's 10 grams for both. The difference is going to be in the molar mass. So the mole mass of water, H2O, is going to be the molar mass 2 times the molar mass of hydrogen plus the molar mass of oxygen. Well, the molar mass of hydrogen is 1, so 2 times 1 is 2. The molar mass of oxygen we've done several times already before. It's 16. So the molar mass of water is going to be 18. Now we want to find the molar mass of ammonia. Is going to be the molar mass of nitrogen plus 3 times the molar mass of hydrogen. So the molar mass of nitrogen is going to be 14 plus 3 times 1 is 3, so that's 17. So the molar mass of water is slightly more than the molar mass of ammonia. So the number of moles in 10 grams of H2O is going to be 10 divided by 18, and the number of moles of ammonia is going to be 10 divided by 17. So this number, the higher the denominator, the lower the number. So let's actually work this out. Work it out as decimal. So 10 divided by 18 is 0.555 recurring, and that's how many moles there are. And 10 divided by 17 is going to be a little bit more than that, 0.588 moles. So which contains more particles? The ammonia. Last question. So we dissolve 117 grams of table salt, sodium chloride, into water to create a solution with a concentration of 4.0 moles per litre. What is the final volume of the solution in milliliters? So let's extract what we've got. So 117 grams sounds pretty much like a mass to me. Concentration, they give it to us. Concentration is 4. And here, quite usefully, they give us the volume as capital V. So we're wanting to find capital V. All right, what don't we have, and what might we need? Well, we don't have the number of moles. We don't really need it. So what I'm going to do, if N equals CV here and N equals M over big M, I'm going to set them equal to each other. So if N equals CV here and N equals this, then this must equal this as well, because N obviously equals N. So the concentration is C, which is 4 times the volume, is little m, which is 117, over big M. Now, we don't know what big M is. We don't know what the molar mass of sodium chloride is, but we can pretty much work it out. So the molar mass of sodium chloride is going to be the molar mass of sodium plus the molar mass of chlorine. If it's with another chemical, it's a chloride. If it's by itself, it's chlorine. And we can work that out. So the molar mass of sodium is 23. And the molar mass of chlorine, is 35.5. And if you can do this in your head, good. It's 58.5 grams per mole if you want to put the unit in there, but we know that it's 58 grams per mole. All right, so that tells us that the volume is going to be this number here, 117 over 58.5, all of that divided by 4. So Mr. Casio comes into his own. So brackets 117 divided by 58.5 is that, and then we're going to divide that by 4. 0.5 watt, 0.5 liters. Are we done? No, we're not, because it wants it in milliliters, and that's going to be 500 milliliters. And we're done. So that's an introduction to those equations. All the best.